Section 3.3, we're going to look some more at growth and decay factors. We talked about growth factors in Section 3.1 and decay factors in Section 3.2. So we're going to expand upon some of those ideas. We're going to talk about determining the growth and decay factor of an exponential function. We're going to talk about exponential functions of the form y equals a times b to the x. In the previous two sections, the a value was missing. It was 1, and now it's going to be not 1. It's going to be some other value, a times b to the x. And then we're going to talk about doubling time or halving time, and those things are going to be themes throughout some of the later sections here as well. Okay, so in our first situation, we have the number of Spotify users from June 2012 to June 2017. So these are all the June users for Spotify. We want to know, does this table represent a linear function? So they're not asking us if it's a function, they're asking us if it is a linear function. If it's going to be a linear function, then there needs to be a consistent slope. So since I have consecutive inputs where the inputs are increasing by 1 each time, I would need to have outputs that increase by the same amount each time. So the amount of increase between 15 and 24 is 9. That's an increase of 9. Then the amount of increase between 24 and 40, that's an increase of 16. So already we're saying that's not the same. And if we continue looking down here, the increase between 100 and 140 is 40, again with consecutive inputs. And so we can see that we do not have consistent slopes. So this is going to be no, because the slope is not constant. So if it's not linear, the question becomes, what is it? So instead, we're going to calculate the following ratios. So ratios are when we divide two quantities. So we're going to, instead of taking the difference, figuring out what you need to add on, this difference was computed with subtraction. 24 minus 15 is 9. 40 minus 24 is 16. Slope is a difference. And then a ratio, it's going to help us determine if this is going to be a multiplicative function. So we're going to divide 24 by 15 to get the first ratio. And then we're going to divide the next pairs to get the next ratio. I'm going to grab Desmos so that I can have some help with these divisions. Let me pull this up and just make it a little smaller so I can see everything at once here. All right, so the first ratio, we want to do 24 divided by 15. So this first ratio is 1.6. The next ratio for 2014 to 2013, that's going to be 40 over 24. So that's 1.67. The next ratio is going to be 75 divided by 40. So that's 1.88. The next ratio is going to be 100 divided by 75, so that's 1.3. And the last ratio of 140 divided by 100 is going to be 1.4. All right, so thinking back to our linear function, for example, the slopes were not constant, so it's not perfectly linear. If they had been close to the same thing, like some of them have been 9, 10, 11, 8, then I might have been able to say that it was approximately linear and that a linear regression would have done a good job. But that was definitely not the case. When I varied from 8 up to 9 up to 40, these values were significantly different. So it's not constant, which means it's not perfect, but it's also not close, which means that a linear regression would not have done a good job. So there's actually two things that we want to mention about that one. Okay. Now here, our ratios are not exactly the same, but can we see that they're kind of close? They're hovering around, say, 1.7 or so. We're actually going to compute the average, but they're close. Okay, so the ratios are close. So they're all between 1.3, and 1.88. Okay. So we're going to compute the average of those now. So we're going to add them all up, and we're going to divide them by 5, since there are 5 different ratios we have here. So I'll move this back over, and we'll do parentheses 1.6 plus 1.67 plus 1.88 plus 1.33 plus 1.4. And like I said, there's 5 items, so I'm going to divide that whole sum by 5. So it puts me in the range of 1.58. Okay. So an exponential function with base b and equally spaced inputs yields output values whose successive ratios are constant. These weren't constant, so this function is not one that would be a perfect exponential, but it could be modeled by an exponential. Later on, we're going to find our base using exponential regression, but right now we're kind of getting an idea of by hand how we might come up with the base for this approximate exponential model. As we saw in the last couple of sections in 3.1 and 3.2, if our base is larger than 1, our function is going to have a growth factor. And if our base is between 0 and 1, our function is going to have a decay factor. And this ratio that we found over here, that's going to end up being our base. Our base is the ratio of consecutive outputs for consecutive inputs. All right, so we're going to use that base of 1.58 on the next page to predict what the number of Spotify users would be. So we're actually going to start with the initial value was 15, as we saw in the previous table. We're going to start with 15. And then since it was the initial value, we're going to multiply by 1.58 to the 0 power. And that's going to be 15 times 1 is still 15. We're going to see how that goes for the rest of them. For the next one, if I did 15 times 1.58, that would give me 23.7. That's not exactly the 24 that you see in the other table, but it's close. So we're approximating the 24 with this 23.7. So our model's not too far off. So we're making a fairly decent prediction for this one. Let's see how the rest of them go. The next one would be 15 times 1.58 times 1.58, or 15 times 1.58 squared. The next one is going to be 15 times 1.58 times 1.58 times 1.58, or 15 times 1.58 to the third. I'm going to use decimals to calculate those values here in a moment. I'll fill in the parts that I came without at first. 15 times 1.58 times 1.58 times 1.58. I need one more, 1.58. And that's the same thing as 15 times, 1.58 here to the fourth. Got my decimal place in the wrong spot there, but we fixed it. All right. When I type them in the decimals, hopefully we can agree it's going to be easier to type them in this form than it would be to type them in the repeated multiplication form. So we'll go over here, and we're going to do 15 times 1.58 to the second. This one gives me 37.4. And I can just change that power to 3. This one gives me 59.2. And to 4, this one gives me 93.5. And if I change it to 5, I can confirm the last one, 147.7. All right, so let's slide this off. All right, so use the pattern for the preceding table to help us write an equation of the form n of t equals a times b to the t for the Spotify function. All right, so n of t equals, the a value in this function is, it's going to be this 15, right? Because we can see that each of these functions are multiplying by 15. that part is constant. We have a 15 that we need to multiply by our base, which is going to be the 1.58 each time to a different power. So our base is going to be the 1.58, and our A value is going to be that 15, which was actually our initial value, our starting value. So our function is going to be 15 times 1.58 to the t. So 15 times 1.58 to the 0, 15 times 1.58 to the 1, 15 times 1.58 to the 2. The input is the exponent on the 1.58. What's the practical domain of this function? All right, so this function is the number of Spotify users, and the input is years since June 2012. So I know that I can have values from 0 to 5. I could probably extrapolate a little bit past 5 as well. And the number of Spotify users is not going to change just in June. So I could predict the number at, say, 1.5. I could predict the number in January or something like that. I could predict in between. So I believe this function should be continuous. And so I'm going to list the domain that way. So I'm going to say that 0 is the smallest value that we would enter into the function. And then we can go 5, 6, 7. We'll say we can extrapolate just a little bit beyond the edge of the data set. In exponential functions, the models break down quite rapidly, so you usually can't extrapolate beyond half the width of the data set. So I might have been able to go to 8 since this is a 3 wide data set. I couldn't maybe want 3 past the edge. Or you could think about half of 5 is 2.5, so I just said 2 past the edge. So 2 or 3 past the edge on this data set gives us a good way of ending our practical domain. We don't want to go very far past the edge to make predictions because they're going to break down quickly. All right, so use a calculator to make the scatter plot of this data for the original function. This is just the original data set first. So let me get my, make this bigger again real quick because I'm on a graph. Let me just clear everything. And make my table. And the table we're typing in here has the 0, 1, 2, 3, 4, 5, and just the original stuff, which was the 15, the 24, the 40, the 75, the 100, and the 140. So let's zoom over on that data. All right, so that's the shape of the data. I'm going to try to sketch in what this looks like. So I've got a dot. What I notice about these dots as I'm drawing them is that they start off with a slow amount of growth, but then the growth increases more rapidly. So I tried to illustrate that here. But I see that the growth is slower for the first several points, and then it starts to increase more rapidly, and that's characteristic of an exponential function. All right, next it says to add the model. Models are equations, so add the equation to the graph. So that was our n of t equals 15 times 1.58 to the t. All right, so I can see it. I know what it looks like. And do I believe that the function is a reasonable model? And I should explain whether I believe this is a reasonable model. So it's really close to the data points. It's not perfect. This point in particular has quite a large gap. And I actually typed that point in incorrectly. I just noticed, my bad, but it still has a large gap. It was supposed to be 75 from the original data, and I just typoed. Then a few of the others are a little further off. Now we could actually see that from the table that we had made as well. The 23.7, that was quite close to our 24. Our 37.4 is not very far from 40, but here at 59.2, we're quite far from 75. Then 93.5 is close to 100, and 147 is a little bit higher than 140, but it's still close. The one with the largest gap was this one, about 59.2 up to 75. That's the largest gap in the difference between the output values. So you can see that registering over here in the graph. Some of these are just a little bit above or a little bit below, but this one's considerably above the graph. But still, I do believe this is reasonable because it fits the center of the data and it is close to most points. There's always going to be a few outliers when you're looking at real data. So this is close to the original data set. I like right here between these 2 points how this model skims the middle. It's not just too high or just too low, but it's an average between the two of them. So we will explain that, yes, we think this is a good fit because it is close to the data. That alone is not enough, but it fits the center of the data. So it's close and it goes between. It's not just all up too high or all too low. It fits the center of the data. Is this the best possible model? Probably not, but we made it by hand. We made it by computing the ratios and by finding the average of those ratios. Had we done a regression, which we'll get to later, we would have been able to find a model that was called the best fit model. Regressions always give us the best fit for a data set based on a more complicated process for finding the ratio and finding the A value. However, this is the best that we can do by hand right here. So pretty good, decent. It can give us some predictions for our data set here. Oh, determine the vertical intercept of the model by substituting 0 in for t. All right. So if I look at n of 0, that's 15 times 1.58 to the 0. And I know that 1.58 to the 0 is 1, so 15 times 1 is 15. That means that the vertical intercept is the ordered pair 0, 15. Now, I can observe that graphically as well. They asked me to do it first algebraically by substituting 0 in, but I can observe on the graph. If I click my model, it's going to go through the point 0, 15. Then they ask me to discuss the practical meaning of the vertical intercept. So the 0 refers to in the starting year. So the starting year would mean in June of 2012. And then there were, the 15 stands for 15 million Spotify users. Okay. All right, in our definition down here at the bottom, many exponential functions can be written symbolically as f of t equals a times b to the t, where a in our case was 15, corresponds with the value of f when t equals 0. So a, another way to say that is a is the initial value, or a is the value in the y-intercept. So we're actually going to make ourselves a note of this as well. When they talk about the initial value right here, a is our initial value, or the y-intercept is the point 0, comma a. I wrote that down just below. There we go. Initial value is our a value, or 0, comma a is the y-intercept. And then we talk about b being the 1.58. Depending on how large that number is, it's either the growth or the decay factor. In this case, it's a growth factor because 1.58 is a base that is larger than 1. Oh, they did go back and mention initial value right here. So the coefficient a is called the initial value like we had said. All right, moving on to the next page. Number 5, use the Spotify function n equals 15 times 1.58 to the t to estimate the number of Spotify users in 2020. So we know that the starting year was 2012. So that means that our t value is going to be 8, since 2020 minus 2012 is 8. So they gave us that hint right here that t is equal to 8. We can always, if that hint was not provided to us, determine what the input would be by subtracting our starting year. So now our goal is to calculate n of 8. So I'm going to use Desmos to compute that, since I already have my function entered over here. We'll ask it to compute n of 8. And so n of 8 is 582.6. So this means that I would just put the word million right after it, just to shorten my explanation on it, since the units on the output were millions. So 582.6 million Spotify users in 2020. Do we think this is a good estimate? Explain. Okay. Well, I'm going to graph this ordered pair here as well. Give me a second to scroll back out. If I graph the ordered pair that is at 8, comma, n of 8. Oh, I got to hit shift. Parentheses. My key was sticking there. 8, comma, n of 8. There we go. All right, so I'm going to label this ordered pair. I gotta find it. Where is it? Whoa, it's way up here. Okay, so it's very far from the edge of the data. The data is way down here. And if you look at how far away this is, remember how I said could maybe go to 7 on my practical domain, because the further away I get from my data set, the farther extrapolated we are. And that's really far away. The distance between this point and this point is more than the distance between the first point and the last point vertically. So this is not going to be reliable. That's not a near extrapolation. That's actually a far extrapolation. It's pretty far away from the edge of the data. So do I think it's a good estimate? I'm going to say no. It's an extrapolation. It's not near the edge of the data set. So do I think this is good? No, because this is extrapolation and it is not near the data set. Okay. Then pause for a second. I'm actually curious. So I'm just going to search real quick for how many Spotify users there were in 2020. And in their fourth quarter, so that's not even June, that's a little bit later, there were 155 million in 2020. So just some further evidence that this was very far off. There were only 155 million. 582 million is a lot more than that. So because we went so far past the edge of the data set, the model it lost some validity. It was no longer able to make accurate predictions. All models will break down, and exponential models break down quickly past the boundaries of their data set. All right, so use the graph of this function or the table feature to estimate the number of years it takes for the number of users to double from 15 million to 30 million. All right, so I've got my graph here still. I'm going to zoom back in on the data set. And 15 million is right here at the vertical intercept. I want to find out how long it takes for it to get to 30 million. So 30 million is an output. So I'm going to graph y equals 30. And I'm going to find out where that crosses our function right here. And it crosses at 1.515 years. So it takes 1.5 years for the function to double. Okay, so it takes 1.5 years to double from 15 to 30 million. Now we're going to estimate the number of years necessary for the number of Spotify users to double again, but this time we're going to double from 30 million to 60 million. Okay. So I already have 30 million graphed. Let's graph 60 million. Y equals 60. All right. So we're at 1.515 and we're at 3.031. And I just want to know how long it takes to get from here to there. So I need to compute the difference in those x coordinates. I want to compute 3.031 minus 1.515. And again, I get 1.516 or 1.5. So it takes 1.5 years to double. Even if I had kept more decimal places and said 1.515 years, 1.516 years, I should get the same thing. There's that one decimal place off, and that's just because these values are rounded when I'm looking at them on the graph. If I had a few more places of precision, I would see that they're identical. Okay, so they should be identical. So to double from 30 to 60 million. So how long will it take the number of Spotify users to double in general? The doubling time in general is 1.5 years. So if I wanted to find out how long it took it to double from 1 million to 2 million, or from 100 million to 200 million, or anything, 20 million to 40 million, to double from any value to twice that value, no matter what the two values are, it's going to take the same amount of time. It's going to take 1.5 years. So note here in this definition that the doubling time of an exponential function is the time it takes for the output to double. The doubling time is determined from the growth factor and remains the same for all output values. So it's constant. I get the same doubling time no matter what I'm doubling between. All right. Then there's an example down here about another function and its doubling time. You can read through. We're going to move over on the next page to our decreasing exponential functions, talking about functions that have decay factors and half time. So we just did increasing exponential functions. They grow, they double. Our decreasing exponential functions will decay, they'll halve. So we're looking at a car here. Its initial value is $22,000. And we've learned that it's supposed to depreciate by 30% per year. And this is the Blue Book value of the car for the next several years. Okay. All right. So in number 7, as the input T increases from 0 to 1, the output decreases from 22,000 to 15.4 thousand. This just says in thousands. I don't know why they wrote it as in thousands instead of in thousands as a word. We usually see it expressed this way. Determine the value that 22 is multiplied by to get 15.4. So the ratio, they were asking us to compute the ratio here like we did before. What is the ratio? And so we always want to compute y2 divided by y1. So we want to do the 15.4 divided by the 22 and compute that ratio. I think I can clear this for the next situation here. So I will take our 15.4 divided by our 22. So I'm going to get 0.659. And they've gone ahead for the next part of the example to round this to 0.7. Okay. And I might have, I apologize. I typed this wrong. I didn't realize it. Sometimes I can't remember numbers and I'm trying to type them back over. It was not 14.5. It was 15.4. So I apologize. Let's go ahead and fix that real quick. It actually comes out right at 0.7. So there was no rounding needed. I just made a mistake when I typed it in the first time. It comes out right at 0.7. So apologize for that. All right, so it comes out at 0.7. And let's take a look at our table. We have the initial value of the car. Initially, it was worth $22,000. So initially, $22,000. And 22 times 0.7 to the 0th power is still 22. Then we can compute the value after 1 year. 22 times 0.7, or 22 times 0.7 to the 1, it's 15.4. And we'll compute the rest as well. 22 times 0.73 times, or 22 times 0.7 to the 3rd, and then 22 times 0.74 times, or 22 times 0.7 to the 4th. Let's go ahead and compute those values. So 22 times 0.7 to the second power is 10.78 or 10.8. To the third power, 7.546 or 7.5. And to the fourth power, 5.28 or 5.3. In this case, the values that I get for my model are going to exactly match the values that we get for this table. This one's not going to be an approximate exponential model. It's going to be an exact exponential model just because of the way this one was constructed. That doesn't always happen from data sets, but it just happens because of the way this data set was constructed originally. Okay, so use the pattern in the table to write the function. So v of t, since they said function, I'm going to put it in function notation, equals a. So my a is the initial value. As you see, each of these has a 22, times b, the base, each of these is a 0.7. To that, the power is changing, so the power is my input variable t. 22 times 0.7 to the t. Input the function into my calculator and graph it. Okay. V of t equals 22 times 0.7 to the t. Now they said over an appropriate window. So my appropriate window should include the initial value up here. And then it doesn't really matter how far it goes, but what I want to see is certainly that initial point at 0.22. And then maybe I can see the first four values. Maybe I don't need to see all the way to the value 30. So how about I cut my x-axis down just a little bit so I only see maybe the first 10 years instead of the first 30 years. And I don't need those negatives. I'm going to put -1 right here just so that the x-axis or the y-axis isn't on the border so I can actually just see it. But I'm trimming down that length right there because I really don't need to see that far into the future what I got when I zoomed out. So I can see my year 1, year 2, year 3, year 4. That was what the data set was able to give me, and I can see a little bit further into the future prediction. So something like this would be an appropriate window on this one, making sure that I can see the initial value and then a few years into the future beyond the initial. Okay, determine the vertical intercept. Write the result as an ordered pair. Well, I can see it on the graph. It is 0, 22. What is the practical meaning of the vertical intercept in this situation? 0 is the initial t value, and that just means when the car was first purchased. So when the car was purchased, or you get rid of most of those words by saying initially, it was worth, and the 22, putting units back on it, means $22,000. You can write 22,000 or just 22,000. All right, I can move decimals out of the way. I just was keeping that graph up there for fun. And we got our initial value. Let's go to the next page. Oops, bumped something there. All right, number 8. Estimate the number of years it will take for the value of the car to be $11,000, and that's half of the original value. Okay. It's an output value, so we're going to graph y equals 11,000. Sorry, y equals 11 because my thing is in thousands. My units on this are in thousands. So this means that I want to find out when I'm equal to 11, since thousands are my units on this. This 22 isn't 22,000. 22 has the unit thousands with it. So I'm going to graph y equals 11, and we're going to find out. So initially, it was worth 22,000. It's going to be worth 11,000 after 1.943 years. Okay. So 1.943 years, or 1.9 years, we go from 22,000 down to 11,000. Okay. Now, I am always comparing the two inputs here, but 1.943 minus 0, since this one has 0 as its initial value, is still 1.943. When I do the next one and I compare how long it takes for it to be halved again from 11,000 down to 5,500, this one I'm going to graph a y equals 5.5 to keep the units in thousands. Then I'm going to have to make sure that I do the difference of the y values so that I can go from 1.943 to 3.887. So 3.887 minus 1.943 is 1.944. It takes 1.944 years to go down from 11 to 5.5 thousand or 5,500. Okay. Now, these values are supposed to be identical. The only reason that I'm not getting the same thing is because they're rounded to 3 places. There's rounding involved in that last digit right here. So I can only get accuracy from a rounded to 3-digit value to a rounded to 2-digit value in my computation. They're both 1.94, or just 1.9 is sufficient in this case. So they should be the exact same thing if I had a little more precision on those values. So we're going to say that they're the same at 1.94 years. And then we can also say that similarly to our doubling time conversation earlier, that the half-life of an exponential model, the amount of time it takes for the model to decay by a half, remains the same for all output values. So it doesn't matter if I'm having from 22 down to 11 or 11 down to 5.5 or 50 down to 25. I can have between any two output values, and the time it would take to have is the same. So given a choice, it's easier to make the computation to have from the initial value because you don't have to subtract the 0. I mean, you are subtracting the 0. 1.943 minus 0 is still 1.943, but you don't have to actually do the subtraction computation to figure out the value because it's obvious when you subtract 0, you get the same thing as the input value. Okay, so there's another example down here talking about half-life in another situation, so you're welcome to look through that one. We're going to take a look down at the bottom for number 9 here. Inflation means that the current dollar value will buy less in the future. So the inflation rate for 12 months from 2016 to 2017 was 2.5%. So a 1 pound loaf of bread in 2016 cost $1.25, dollar 1.025. So they rounded it this 0.25 up to $1.03 because you can't have a 0.5 of a cent. So they did round right there. But the change in price is usually expressed as the percentage rate known as the inflation rate. Okay. So now we're going on to this situation here, assuming that the inflation rate remains at 2.5% per year for the next decade. We're going to calculate the cost of a pizza, which currently costs $12 for each year over the next decade. Complete the following table and then round our results to the nearest cent. All right. So first of all, our pizza costs $12, and we need it to cost 0.0. Oops, I wanted the parenthesis in the other direction. 2.5% more, which is $0.025 more. So I want it to cost 30 cents more. So I can do 12 plus, might as well just put in the 12 plus here, 30 cents. And you can see that our pizza is going to cost $12.30 1 year later. So not a ton, but still 30 cents more. Then we're going to take our $12.30 and we're going to do the same thing. We're going to still have inflation of 0.025. So now it's going to cost about 31 cents more, right? So if I add on the $12.30 to this, you can see it would be $12 and 61 cents. Okay, then again, our $12.61 times our inflation rate plus our $12.61. Now it's $12.93. Okay, do a couple more of these. Oops. $12.93 times our inflation rate plus the $12.93 puts us at $13.25. Okay, so $12 pizza 4 years later is $13.25. I'm going to do one more of these. I'll fill in the rest of the table once I have the function so that it saves me time. But you get the idea here. So I've got my $13.25 times the inflation rate. Means it's going to cost an additional 33 cents this time, plus the $13.25 is now $13.58. So it went up by 30 cents the first time, 31 cents the next time. It's not going up by a lot more each time. This time it's only going up by 33 cents compared to the 30 it was originally. So it's going up by just a teeny tiny bit more each time. Okay. All right, I'll come back and fill those in a bit. So you can keep going and fill yours in and then we can compare in a moment. Now, the next couple steps they want me to do is determine the initial value. So the initial value is the value for time 0. It's also called our A value. So our A value is going to be 12 because the initial value of this pizza is it cost $12 in the first year that we were considering here. Determine the growth factor by dividing consecutive inputs. So we're going to do this a couple times just to make sure. So we're going to take, say, 12.30 divided by 12, find out what we get. And then maybe we'll also take one of the later ones. Let's take our 13.25 divided by our 12.93. So it's just a y2 divided by a y1 wherever we're at. We're dividing the second y by the first y in consecutive pairing. So I'm just going to do 2 of them just to make sure that I get something that's similar from each of my ratios because the growth factor should be the same thing no matter which 2 I'm looking at. Okay. So in the 12.3 divided by 12 case, I get 1.025. And in the other case, 13.25 divided by 12.93, I get 1.0247. So we're going to call that 1.025 if I'm running them both to 3 places. Now, if I had kept more decimal places on the 1325 and the 1358, like it was 1358, 125 after it, I actually would have gotten exactly the 1.025. But because of the rounding, we're still very, very close. And even to 3 places, they do round to the same value. All right, so this means that our growth factor, which is B, I'll write it off to the side, our B is 1.025. Okay, so together, that gives me what I need to write the equation. To write the equation, I need to know the A value and I need to know the B value. So our equation, C of T for the cost of pizza, is going to be of the form A times B to the T. So A is 12 times B is 1.025 to the T. All right, so now I'm just going to go back and fill in the rest of those equations, those numbers up here, so I can use the formula for it. Just makes it a little faster for me while I'm doing my video. You can fill them out by hand and just compare. So C of T is 12 times 1.025 to the T. And I can evaluate C of 6. And this one would be 13.92. And C of 7, this one would be 14.26. C of 8, 14.62. C of 9, 14.99. And 10 years later, 15.36. You can also just go back and check for any of the other ones, like C of 3, for example. I can see matches up with my 12.92 here. It wouldn't be 9.3, but again, I had already rounded on this one, and that's where a little bit of rounding had started to play in and happen there. So you might get slightly different things because you have been using rounded values along the way. They should be pretty close. Okay. So all right, explain the meaning of the A values and the B values in the situation. So in the future, by the way, we're going to want to write the equation first and fill in our table if you're worried about like when rounding is going to matter. But right now, we're more filling out to the table by exploration and then using it to help us get the function. In the future, we'll try to write that function a little earlier, then fill in the table with the function. Okay, so meaning of A and B values. So A is the initial value. Initially, this was what year? Number of years from 2020. So the A value means in January of 2020, the pizza costs $12. That's what the A value means. So initially, but to quantify what initially means, what is the initial year, the initial date? It's January 2020, as we can see up here at the top. The pizza costs $12. That's what A means. It's our initial value. And then B is our growth factor. And I'll talk about growth factor. I want to sneak in growth rate here as well, because that is what's coming up in section 3.4 and it ties in right here. So if I was going to explain this in terms of growth factor, I would say that each year the cost increases by a factor of 1.025. Now, that's not as straightforward as you might use words like this in normal conversation. In normal conversation, you would actually probably talk about this growth factor in terms of its growth rate. The growth rate is the rate at which you grow above 1 being no change 100%. So this has an R value, a growth rate of 2.5%. So we'll just mention this. We're going to define these a little better in the next section. Our growth rate is our R value, and our growth factor is our B value. If I wanted to explain this in terms of a growth rate, I would say each year the cost increases by 2.5%. Or I might have phrased that backwards and said the cost increases by 2.5% per year. And that's actually how I would more traditionally say it. I would put the per year or the each year at the end. Usually, I just kind of mimicked what I had right here as well. And I think that it's a little cleaner to talk about those two, to talk about the initial value and the growth rate. And we'll be doing that starting in section 3.4. So just previewing for that a little bit here. Okay, determine C of 5 and interpret the result. So I still have my function and I can plug 5 into it. C of 5 is 13.58. That matches what I have in the table once I round it to the nearest cent. That's perfect. And interpret the result. So that's 5 years after 2020. So my interpretation would say in, oops, I should put in January here since this was, the January prediction was the whole number. I could predict for June if I did something like 5.5, say, or 5 point, whatever the decimal, it's 5.5 would get me in June halfway through the year. But in January 2025, the pizza costs $13.53 due to inflation. Okay, graph the function. All right, I've already got it typed, so it's already graphing. I just can't see it yet over here because the scaling is not right. I'm going to rescale this like they asked me to. with a negative 20 to 20 on the independent variable and 0 to 20 on the dependent variable. Okay, so I can see the function here. And it should look like an increasing exponential function. Especially if you zoom out, you can see the increasing exponential function that's super flat up to steep. In the previous window that they wanted us to have right here, I can still see it's got a slow increase followed by a more rapid increase over to the side and on the right. Is the entire part of the graph here relevant to the original problem? So they did ask me, and I was curious about that. They did ask me to graph this on the interval negative 20 to 20. And so this is not all relevant because the negative stuff isn't relevant in this case. I'm sorry, I moved my graph out of the way. Right? And so we would say that no, the negative 20 to 0 portion, half of this independent variable part is not relative or relevant because it's previous to the initial value. It shows predictions for previous years. Okay, so then now that we think about that, they're going to ask us to fix it. So we're going to fix it and now look at just the years from 0 to positive 20. So we're going to split that independent axis in half and cut this down to 0 and regraph. Okay, so now we're seeing the same graph, but we're looking at it just from 0 to 20 on the t-axis. It's not flat. I know it almost looks linear on this window. Don't draw it as a straight line. There's a little bit of a curve here. It is increasing. There's a little bow, a little curve, and it gets higher on the right-hand side. If you can't see that, just zoom out until you can see how the pattern is going to look. It's doing that even on that smaller window. All right. I may have exaggerated the curve in my drawing, but there is some curve there. That's what I want to say. Okay, almost done. The last little piece here. How many years will it take for the cost of the pizza to double? Okay, so we already saw that we want to double from the initial value. The initial value is what? It is 12. So I know that since A is 12, if we want to double, we want to find out when Y is 24, twice 12, right? That's going to be double the initial value. So when is the output, Y? Twice the initial value. So 2 times 12 is 24. Let's find out. And it's going to take 28.071 years, or we can round that to 28.1 years. It takes 28.1 years to double. Now, because I used the initial value and the 24, I'm really doing 28.1 minus 0 because 0 is the input value for this one. You're always subtracting something to calculate how many years. But because this was the initial value, it was at 0, 12, so 28 minus 0 is still 28 years to double.